Welcome back. So we're going to start our discussions about mild analgesics. In particular, we're going to focus on aspirin for this because this is the main accessible item for the IB, but we'll also have a bit of a discussion about other mild analgesics such as ibuprofen and paracetamol. So if we look at this diagram here, it gives us an idea of the different analgesics that we deal with in terms of pain. So when we're talking about mild analgesics, we're looking at this non-opioid pain relief at the lowest level here. Generally looking at things that have a larger therapeutic window, making them safer and better for individual management of pain and low-level pain. So mild analgesics come under two main classifications, those being NSAIDs, which are non-steroidal anti-inflammatory drugs, because you can have steroidal ones as well, which we don't actually look at. These are generally of and acetaminophen, which is paracetamol, generally Tylenol or Panadol or things like that. So non-steroidal anti-inflammatory drugs include aspirin and ibuprofen. Acetaminophen is a different classification of pharmaceutical product. Paracetamol works in a different way. All of these are generally over-the-counter medications, so you can buy them supermarkets or over-the-counter at your pharmacist or things like that. So there's not a lot of restriction around who can buy these or really even in what quantity. So ibuprofen you can buy from like Chemist Warehouse or somewhere like that in 96 tablet bottles. So they're not really controlled. They're non-narcotic, which means they don't tend to cause euphoria or act in our brain. So they are acting on that first pain mechanism that we talked about, where they are working at the site of the nociceptors and the prostaglandins. In this case, they inhibit prostaglandin release. So prostaglandins are the ones that are released when pain signals are first noticed, and then those prostaglandins bind into our nociceptors, sending the pain signals to our brain. In this case, they're inhibiting the prostaglandin release, so they're stopping those prostaglandins from being released and working on our nociceptors, pain receptors. You can see here we've got the structures of each of them here, where we have aspirin, which has our phenyl aromatic benzene, an ester functional group, and a carboxylic acid. If you're not familiar with your functional groups, please make sure that you review them. Being able to identify different functional groups in our pharmaceutical products is a key aspect that we need to be able to do in our option. Paracetamol, you can see, has the same kind of phenyl ring here, but instead we have a free OH. So this is a phenolic. It's got an OH attached to the benzene, the hydroxyl. We have an amide, C double bond O and H, which is our carboxamide or amide group, the simple carbonyl here, and the hydroxyl. Ibuprofen, you can see we have similar structures again. All of these molecules have fairly similar structures because they're going to bind to the same kind of receptors. In this case, the receptors that are responsible for releasing promoting prostaglandin release. Aspirin, as I mentioned, is the one that we need to look at in the most detail. So aspirin's been known since around 400 BCE, where willow bark was chewed for the treatment of pain and fever, and it's been recorded back thousands of years. In the 1800s, they were able to show it being the active ingredient salicin, which is then converted into salicylic acid in the body. So this is salicin here on the left here, and then this is what is extracted from willow bark, and then this is the active salicylic acid, which is converted from salicin to salicylic acid in the body. It wasn't until 1897, so in the 19th century, that Felix Hoffmann, who was a German chemist working for Bayer, and you'll remember if you look at Dispirin here, it typically has been produced by Bayer for a long time. They modified the hydroxyl group into an ester functionality, which forms the acetyl salicylic acid, which is what we know as commercial aspirin. So this side chain modification here, where we've esterified this group here, is what has taken it from salicylic acid to what we buy now and what is produced as aspirin. You do need to be familiar with the synthesis mechanism for aspirin. Okay, generally we use ethanoic anhydride for the production of aspirin, and we'll be doing that in our lab. This is essentially the condensation reaction between two ethanoic acid molecules. This is just simply a more efficient way to provide ethanoic acid into the reaction mechanism, because we're still looking at an esterification between a hydroxyl group and a carboxylic acid group, this one here, to form the ester. Okay, so we have a hydroxyl with essentially what will form a carboxylic acid, forming the esterification reaction, and we will reform ethanoic acid during this process. We will, as I said, synthesize it. The procedure doesn't produce a 100% pure sample. Okay, we've talked about how reactions don't always go to 100%. We've talked about equilibrium and various factors that can limit the yield of a reaction, which means that if this is the case, it's not going to be purely acetylsalicylic acid. We're likely to have some ethanoic acid left behind, some salicylic acid, maybe some byproducts and other things like that. So we can't presume that the compound that we have is 100% pure. So we will look at some ways that this can be purified in order to improve that purity, and ways that we can test the purity of the aspirin. So the purification is generally done via recrystallization, okay, and this is based on solubility. We will take our impure sample and dissolve it up into a hot solvent, remembering that solubility increases with temperature for solids. That dissolves everything. Then as it cools, the product, we have different solubilities between the impurities and the product. And as it cools, we should see either the impurities crystallize out or our more pure product crystallize out, remembering that we have different solubilities. In this case, when we do our recrystallization, we should be seeing the aspirin crystallize out first. So recrystallization is a method by which we use different solubilities of the components of our mixture in order to form solids of a more pure product through crashing them out of solution. Once we've done that and we dry them, we can determine the melting point. Because the melting point of compounds is generally characterized when we know that they're pure, so if we make a new compound, one of the ways that we need to characterize it when we publish that it's a new compound is that it's published with the melting point, and we determine the melting point using a melting point apparatus, which uses these little tubes here. The wider the range of the compound, so how many degrees that it melts over, gives us an idea of the purity. The sharper the range, the less likely it is to contain impurities, and then we can compare our melting point of our crude product to the known melting point of aspirin. Okay, so in this case, if we look up the literature value in our booklets and reference booklets, we would find that the melting point for aspirin is 138 to 140, and the melting point for salicylic acid is 159. So if we were to get the melting point and find that the melting point was closer to 159, then we would know that our product hasn't really formed and we've got the majority of starting material. The synthesis hasn't been successful. However, if it's closer to 138 to 140, we can be pretty certain that what we've made is more likely to be aspirin and not the starting material that we started with. So comparison of melting points gives us an indication of the purity of the substance. There's a couple of ways, and we will look at a colorimetric way, so using a color test. We'll use one using an iron solution, which turns purple or yellow for salicylic acid, or the acetylsalicylic acid, which is the aspirin. So there are a number of ways that we can test the purity of a substance to get an idea. One of the other things that we can do is we can run a infrared spectrum of our sample. Now we will look at infrared spectroscopy more when we look at the theoretical aspects of the measurement unit when we do spectroscopy, and we'll even be going, hopefully we're trying to a Melbourne Uni to see how these machines operate. But for now, what you need to be able to do is compare the infrared spectra, and we'll talk a little bit more on how these are obtained in class. But IR spectroscopy can identify the different types of bonds that are present in a molecule. So it allows us to identify functional groups. And we get these characteristic peaks dependent on the type of bonds that are there. So this peak here at just above 1500, around 1600 wave numbers, is indicative of C double bond O. If we have a look at the bottom one here, we can see that we actually have two. This is the C double bond O of the acid, of the acetylsalicylic acid, and we have that in the salicylic acid as well, whereas the green one here is the presence of the ester. So because we have both, we know that this one is aspirin, because we have both the C double bond O OH of the acid moiety as well as the ester. Okay, so this C double bond O is the green one, and then this one is the orange one. In the case of salicylic acid, we only have the one because this group here is still a hydroxyl and not an ester. Okay, this OH here is shown here by the acid, and here again it's present in both, but the OH that we see in the phenol, the phenolic alcoholic OH group, which we see up here above 3000, is only present in the acetylsalicylic acid because we've lost that group when we form the ester. So this is sort of like an exercise in pattern matching to go, well, I can see these groups present in this one that aren't present in my salicylic acid sample, whereas I can see the ester group here and the OH group here. So we look for these key differences, and we'll talk about this a lot more, particularly for higher level when we look at structure identification. For now, you should just familiarize yourself with the key differences between the two spectra for these two compounds in particular. So aspirin actually is delivered as acetylsalicylic acid, but it's salicylic acid which is active in the body. What happens is this acetylsalicylic acid is relatively tasteless and therefore has higher patient compliance, is easier to take, and it's easier on the stomach than salicylic acid. But once it passes through the stomach into the small intestine, the ester is hydrolyzed using a base hydrolysis because the small intestine is slightly basic, and the water present in our cells, it hydrolyzes to salicylic acid and ethanoic acid. This is processed by our body, and then this is absorbed into the blood plasma and carried towards the site of the pain. So as you can imagine, we've talked about bioavailability. We talked about how the preparation of a salt can increase the polarity of the compound and therefore promote its uptake into the body. So aspirin, while it has these polar carboxylic acid groups on it, its solubility is increased by producing a sodium salt. And most of the formulations that are on the market these days are sold as salts. They also have different coatings on them to help buffer them from the stomach acid and different other things like that that are put in with the tablet. But most importantly, we have this alteration of the carboxylic acid functionality into a salt to increase aqueous solubility and therefore bioavailability, remembering that this ester group here is cleaved in the small intestine and reforms that hydroxyl in the small intestine. So just a quick look at paracetamol, because aspirin is the one we need to know mostly about, but they may show you things like paracetamol and get you to compare the structures or things like that. So we'll just have a quick look at it. It's more likely to be prescribed to pregnant women and children because it doesn't have the side effects of blood thinning and things like that. However, over the last, not even a few years, but for a while now, we've known that paracetamol is hepatotoxic, which means it's toxic to the liver. It's not the paracetamol itself, but the breakdown products, and paracetamol is broken down very well by our liver. So the products that it forms when it breaks down are actually toxic to our liver, which isn't great. If we take it with alcohol, then the toxicity is increased. Okay. And we can have quite severe issues with this. So it is very important, particularly with things like paracetamol, to not take more than the recommended dosage, because it does have this liver toxicity. The thing about paracetamol is its mechanism of action is different to other mild analgesics, so it's not said to be a non-steroidal anti-inflammatory, which is what aspirin and ibuprofen fall under. This is ibuprofen, which is another non-steroidal anti-inflammatory like aspirin. So it has a slight blood thinning effect as well, and inhibits the formation of prostaglandins by inhibiting these enzymes here and the arachidonic acid pathway. Again, you don't need to know these pathways in detail. They won't be assessed. It has lower water solubility, so again is often produced as a salt, and in this case it's usually a lysine salt rather than just a simple sodium salt. So just a couple of advantages and disadvantages. Okay, so aspirin actually has greater numbers of side effects than paracetamol. Some of those side effects are beneficial, like thins the blood, reduces blood clotting, or can be beneficial depending on what we're using them for. It will also reduce swelling and inflammation, which doesn't occur as much with paracetamol. It is important to remember, though, that aspirin also has a synergistic effect with alcohol. So taking aspirin with alcohol enhances its effects. So it's important because that will also enhance the side effects. So with a lot of drugs, you need to be very, very careful about the effect that alcohol and other things can have on the action of the drug itself. So just one last little bit about aspirin in terms of its side effects is that we need to be aware of the prophylactic effects of aspirin, and by this we mean the protective effects. So it is a good case study for us to understand that side effects can be both beneficial and negative depending on the situation. So aspirin was not really used for its anticoagulant properties. Once they were discovered, it's been now prescribed a lot as a mild form of anticoagulant or blood thinner to help relieve some of the problems associated with heart disease. So the blood thinning and anticoagulant properties of aspirin are prescribed for people with high risk of blood clots, which can lead to strokes, or just prescribed for people to take a low dose of aspirin following surgery to allow for minimizing the threat of things such as blood clots. Okay, so if we think about the term prophylactic, it is a treatment that is taken to prevent disease rather than treat it. So these are prescribed to prevent blood clots or to try and reduce the risk of heart attack or reduce the risk of stroke. Okay, and just another point to remember, that when aspirin is taken with alcohol, there's a synergistic, so this means to work together. Okay, which generally form an enhanced effect, which causes side effects of aspirin to be enhanced. So we can see increased stomach bleeding or ulceration, which are some of the more negative side effects associated with aspirin. Okay, so this one's just if you want to watch another video on pain to better understand it. I recommend this one here, which is from the SciShow, and after that we will move on to talking about strong analgesics.